Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist that I'm calling Continuous Random Variables. Let's jump to today's topic, which is a gamma distribution. Now, the gamma distribution is a two-parameter family of continuous probability distributions. The exponential distribution and chi-square distribution are special cases of the gamma distribution. There are two equivalent parameterizations, with a shape parameter of alpha and a scale parameter of beta, with a shape parameter alpha and an inverse scale parameter 1 over beta called a rate parameter. In each of these forms, both parameters are positive real numbers. And in R, you can use either of these parameterizations, but you have to know which one you want, and you have to set the parameters in the right spot. So the definition of a gamma distribution, and we're going to use the first one, the shape parameter and the scale parameter beta. For any positive numbers, alpha and beta, the gamma distribution is defined as this. F of x is beta to the alpha divided by gamma of alpha, x to the alpha minus 1, e to the minus beta x. This is for all positive x, and it's 0 otherwise. Now, if for the second definition, the beta just would be moved to the denominator. Let x be a gamma random variable with parameters alpha and beta. The mean of x is given by alpha over beta. So the definition, e to the x, is you take x times the density integrated over all possible values. Well, we take the x's into each other, and that's what this x, alpha plus 1 minus 1, e to the minus beta x comes down. We multiply it by 1. This beta to the alpha plus 1 and the gamma of plus 1. We multiply and divide by those quantities. And we do that because this makes another gamma distribution, which integrates to 1. So it goes away. Here the beta values cancel, leaving just beta. We use the recursive formula for gamma, and that becomes alpha times gamma of alpha. Gamma of alphas cancel. We get alpha divided by beta. That's what we wanted to show. Let x be a gamma random variable with parameters alpha and beta. The second moment of x is given by this equation, alpha times alpha plus 1 divided by beta squared. And now this is a sort of a rinse and repeat proof. The expected value of x squared, the second moment of x. You take x squared times its density integrated over all possible values. The x's combine into this. Everything else comes down. We multiply by 1, a well-chosen 1. Then this piece looks like another gamma distribution with parameters alpha plus 2 and beta. This integrates to 1. We get cancelizations on the beta. We use the recursive formula for gamma twice. Gamma of alphas cancel, and we're left with the appropriate equation, which is what we wanted to show. Let x be a gamma random variable with parameters alpha and beta. The variance of x is given by alpha divided by beta squared. We're going to use the working definition of the variance of x, which is e to the expected value of x squared minus the mean squared. Plug in the values that we achieved up there, simplify it, and we get the appropriate answer, alpha over beta squared. Let x be a gamma random variable with parameters alpha and beta. The moment generating function of x is given by, mx of t, which is e to the expected value of e to the tx, which is this quantity here, beta over beta minus t alpha. The proof is this: the expected value of e to the tx, you take e to the tx times the density integrated over all possible values. We combine the e's and get this here. Well, this sort of looks like another gamma distribution with alpha, and beta would be beta minus t. So if we had the appropriate constants, it would integrate to 1. So we multiply by a well-chosen 1. to make this integrate to 1, which are these here. So, of course, this comes down, and this is what was, the reciprocal of what was needed for this to integrate to 1. Gamma alphas cancel. We combine these two into this, and that's what we wanted to show. Now, let x1 through xk be independent gamma random variables with parameters alpha 1 through alpha k and beta respectively. Then x, which is the sum of these independent gamma random variables, has a gamma distribution with alpha and beta, where alpha is defined as the sum of these alpha 1 through alpha k. So this would be the moment generating function. So let's prove it. We're going to use theorem 6 from video ims29. So that's the 15th video in the playlist Introduction to Mathematical Statistics, which is on moment generating functions. And it says that when we take the expected value of e to the tx, but it's the sum of independent random variables, then it becomes the product of those moment generating functions. But each of those moment generating functions is a gamma random variable, which we showed was beta over beta minus t raised to the alpha minus, or alpha I. But that product ends up just summing these exponents. And then we were calling that alpha, and that's what we wanted to show. So the sum of independent gamma random variables is itself a gamma distribution. Now, a graphical illustration of the gamma distribution. The code is not important, but I will post it for you to review. Here are possible gamma distributions. With different alpha and beta, these are the different shapes that are possible. And there are, of course, an infinite number of combinations. And I think that's all I have for this video. Yep, the next video will be on the exponential distribution, which is a specific case of the gamma distribution. We're at 7 minutes. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.